Right. Let us move into the next section, which is the aircraft propulsion. Okay, earlier I didn't mention whether it is for aircraft application or land-based application, but you can see from different type of example for the open cycle as well as the closed cycle, you can already see there are examples on both the aircraft as well as the land-based gas turbine. Let us move into the aircraft propulsion. The greatest impact of gas turbine has been in the field of aircraft propulsion. So this is just an example of the first experimental Whittle engine in 1937. Okay, it is quite a classic engine designed by Sir Frank Whittle and built by Power Jets Limited, Whetstone. So you can see here it is like a compact engine, right? So you have this is the direction of the flight, okay, the air intake there, okay, air being supplied into the system, okay, from here, okay, air being supplied, okay, and then you have the compressor there, right, the compressor blades, okay, and if you see the blue color, if you can see the blue color, this is just a color of the air flowing through, right? This is a single shaft, the main shaft, right? Before the air being supplied into the combustion chamber. So air coming in, okay, then being supplied to up here, going into the combustion chamber, okay, okay, and then combustion process took place and the air being supplied to the turbine stages. There only one single stage of turbine, right, and then being flow into the nozzle, exhaust to the environment. Okay, it's quite good model for learning on the propulsion for gas turbine engine. This is another example, Rolls-Royce Olympus jet engine, which was the first twin spool engine in production and being used in the Vulcan bomber as well as in Concorde supersonic transport. So Olympus turbojet engine courtesy by Rolls-Royce. So you can see so many pictures or history about this particular engine. This is the first twin spool engine in production, right, being used in Concorde. And the Olympus also being used as a gas generator. Apart from aircraft propulsion, it's also being used for turbine to drive power turbine, okay, for land-based power turbine, as well for both electricity, and also being used in ship. It is also being used in marine propulsion. So it's not the same gas turbine engine can be used for land-based as well as the marine propulsion application. So this is another picture of an Rolls-Royce Dart engine. It looks like a dart, so that's why it is called the Dart engine. Okay, for low-speed aircraft, a combination of propeller and exhaust jet provides the best propulsive efficiency. Okay, and figure 1.10, okay, this is particular figures, shows a single shaft turboprop engine. So Rolls-Royce Dart, and it uses a centrifugal compressor. So this particular engine uses a centrifugal compressor, which is situated here. This is the compressor stage. And there are two stages of compressor. Okay, and also they use can type combustion chamber, right? The Rolls-Royce Dart engine started service in 1953. Okay, the power output is 800 kilowatt, and in steel production, it is still in production until 1985. You can see that it is more than 32 years of span of the usage of the engine, with the latest version at 2,500 kilowatt. So starting from 800 kilowatt, they can move the engine, they can upgrade the engine up to 2,500 kilowatt. So this is the can type combustion chamber, right? And these are the two stage of centrifugal air compressor, and these are the turbine stages. The turboprops are also designed with free turbine driving propeller or propeller plus low pressure compressor. So this figure 1.11 shows the Pratt and Whitney Canada PT6, right, which uses a free turbine, okay, and the use of a combined axial centrifugal compressor. So this is a unique engine where it has centrifugal compressor, okay, and then they also install axial compressor, right, and a reverse flow annular combustor, okay, can also be seen here. So like the first Whittle engine, it is a reverse annular where the air being supplied reverse in a reverse mode for the combustion chamber to occur. Sorry, the combustion process to occur. The available power for this type of engine is a range from 450 kilowatt to 1,200 kilowatt, which is suitable for single to four engine short takeoff and landing aircraft. So short takeoff and landing aircraft, you may require this because remember, what are the advantages of having a centrifugal flow compressor, having an axial flow compressor? For this type of engine, they combine both the centrifugal flow compressor as well as the axial flow compressor. Okay, that's why it is very suitable for short takeoff and landing vehicle. At high subsonic speed, a propulsive jet of smaller mass flow but higher velocity is required. Okay, this was originally provided by turbojet engine, okay, but can now be superseded by turbofan or bypass engine. Part of the air delivered by the low pressure compressor or fan bypass the core of the engine, high pressure compressor combustion, as well as the turbine to form an annular propulsive jet of cooler air surrounding the hot jet. And so, for example, like being shown here, an example of a small turbofan engine, the Pratt and Whitney Canada JT15D, right? This result in jet with lower mean velocity, which provide better propulsive efficiency and reduces exhaust noise because you have a bypass flow of air that will then rejoin the main core air coming out from the exhaust, okay, which can also provide better propulsive efficiency and also can be able to reduce the exhaust noise. A twin spool arrangement is used in this particular type of engine with high pressure centrifugal compressor and a reverse flow annular compressor. So you can see here this outer arrows is the bypass flow, okay, that does not go into the main core of the engine, and there are also air being bled through into the core of the engine, right? Like this particular case, and then the air then perforated goes into the combustion chamber before being supplied into the turbine stages, the compressor turbine stages, like that. Okay, and then the hot air gases will flow into the nozzle area before joining back with the bypass flow. So the flow must be diffused from a high tangential velocity to a low axial velocity at the entry of the combustor. So you can see that the air turn back. It has to be diffused, okay, from tangential velocity to a axial velocity. Okay, this is another figure, a more modern engine, right? Where figure 1.12 or 1.12b, large twin spool turbofan engine, okay, by International Aero Engine. It shows an advanced turbofan design for use with large civil aircraft, For example, like this is the V2500 engine. It is designed for low fuel consumption, high bypass ratio, and high pressure ratio. Right? The turbo machinery are all axial type and a straight annular combustion chamber being used.